can summarize it. Basically, in this topic, we have two categories. Number one is the D block elements, then we have a transition element. So how can I differentiate between the D block and transition element? So of course, I have period 4 like scandium to zinc. So scandium is 21 and zinc is 30. So D block element means that whose outer electron is in the d orbital. When you will be writing the configuration for scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and then zinc, like 21 to 30. So you will see that all the elements, all the elements are having their outer electron is in the d orbital. So I would say they are the d block elements. And you know, D block elements are present in the mid of the periodic table, 21 to 30. It's in period 4. But the thing is, what is transition element? Transition element means I would be considering the same thing, but I would be looking at the unpaired electrons. If it has unpaired electron, so I would say that it's going to be the transition element, and if not, so I would say that it's not a transition element. But remember, transition elements must have unpaired electron in their ionic state. This is very important statement. In their ionic state. Okay, in their ionic state. Ionic state means it's a neutral element. I won't be looking the configuration of the neutral element. No, in its ionic state, like scandium is +3, titanium is +2, vanadium is +3, chromium is +3, copper is +2, zinc is +2. In the same way, we have manganese as well, cobalt as well. I have taken some of the examples. So what is the transition element that must have incomplete D subshell? I can also define incomplete, incomplete, incomplete D subshell. So this is going to be the transition element simple, or or let's check scandium. As this is the general configuration for scandium, it's 3d1 and 4s2. When scandium would be having +3 charge, so +3 means we have to remove 3 electrons. So I would be removing 2 electrons from 4s and 1 electron from 3d, so it would become 3d0 and 4s0. If you can see in its ionic state, that is +3, in its ionic state, is there any unpaired electron? You will say no. Why? Because 3d is 0. Because 3d is having no electrons. So yes, it's not a transition element. It's only a d block element. This is one of the reason. This is one of the reason scandium would be forming colorless compounds. I mean to say white compounds. They will not be colored even. Why? Because scandium is not a transition element. It's same as sodium chloride. Sodium is not a transition metal. That's why sodium chloride is a white solid. It's not colored. If you remember the color of copper sulfate, I'm talking about hydrated copper sulfate in which copper is +2, in which copper is +2. So copper +2 is a transition element. That's why it forms colored compound. This is the reason copper sulfate is blue in color. In the same way, we have nickel, we have cobalt as well. Some are green, some are blue, okay, some are pink. In KMnO4, you remember KMnO4, it's an oxidizing agent. Mn is +7. So KMnO4 is purple in color. If you remember K2Cr2O7, potassium dichromate, it's also colored, it's orange. So, so the thing is transition element forms colored compound, but when they have unpaired electrons, so you have to check, is there any unpaired electron or not? If you can see titanium, so yes, titanium also has unpaired electron 3d2 after losing 2 electrons. This is the original configuration for titanium, and this is the configuration when it has lost two electrons. So it has is still two unpaired electrons. So yes, I would say that titanium is a transition element. Then same goes for vanadium. After giving three electrons, still it has two unpaired electrons. So yes, I would say vanadium is also a transition element. But if we can see chromium, of course, when we used to write electronic configurations, so we used to have two exceptions. First was chromium and another was copper. So this is the wrong configuration for chromium, as we know that this is going to be partially filled, which is incomplete. It's unstable. So how can I make it stable? So one electron is going from 4s to the 3d so that they both become stable, because we have two types of stable orbitals. Whether the orbital is fulfilled and whether the orbital is half filled. Whether the orbital is half filled. So if you have any one of them, if you have any one of them, so yes, you will say that it's going to be the stable orbital. So it's neither fulfilled and nor half filled. It's neither fulfilled and nor half filled. How can I make it stable? One electron would be going from 4s to 3d. Finally, it would become 3d5 and 4s1. 3d5 and 4s1, both are unstable. Yes, they are stable orbitals. So whenever it would be asking to write down the configuration for chromium, so we would be writing directly this configuration, not this one, not this one. So like you are not supposed to show how it's going to be stable, how it's going to modify from this one to this one. No, you have to write directly this configuration. This is the stable configuration in which we have half-filled orbitals. So then what's the charge on chromium? Common oxidation state of chromium. It's +3. So when chromium is +3, it means that I have to remove three electrons. So one electron is removed from 4s and two electrons are removed from 3d. So the 3d would become 3d3. So the 3d would become 3d3. Again, I would say there are three unpaired electrons in the 3d orbital. So yes, chromium 3 plus is a transition element. Simple. You can also check copper. You can also check copper. This is the common configuration, like after getting stabilized. It's a normal configuration for copper in which 3d is 10 and 4s is 1. Then copper has a +2 charge. I have to remove two electrons from the copper. So after removing two electrons, copper becomes 4s0 and 3d9. So when I drew the 3d9, I saw that there is one unpaired electron. There is one unpaired electron. Yes, it has unpaired electrons. So I would say that it's a transition element. So that's the reason when we see the compound of copper, it's going to be copper sulfate. It's blue in color. Why the color is blue? Because it's a copper compound and copper is a transition element. Then we have zinc. Zinc means it's 30, proton number is 30. So the full configuration is 3d10 and 4s2. This is the full configuration for zinc. And generally the charge on zinc is +2. So we have to remove two electrons from the 4s, of course, because whenever you are going to remove an electron, so you have to remove electron from the 4s first. You have to remove electron from the 4s first, and then remaining electron should be removed from the 3d as well, right? This is the concept. So zinc is +2. I have removed two electrons from the 4s and 3d remains same. That is going to be 10. If you can check it, there is no any unpaired electrons. All the orbitals are filled. Like, every orbital must have two electrons in it. So all the orbitals are fulfilled. Okay, so yes, copper is not, zinc is not a transition element. That's the reason zinc forms white compounds. They are not colored even. Why? Because zinc is not a transition element. So this is the brief introduction regarding the D block elements and transition element. Okay, so um, so I can say there are only two elements in the 3D series, like I'm talking about from proton number 21 to 30. Only the two elements we have that are not a transition element, that is going to be scandium and then zinc. And then afterwards, uh, and then we have to discuss d block d orbitals basically. So what are d orbitals? Because we have to discuss the color theory. You know, we have to discuss the color theory, why this is colored, why this is not colored. So we must know about the orbitals basically. If you remember, when we used to write configuration for any of the element, let's suppose I have phosphorus. So phosphorus is 15. So when you will be writing the configuration for phosphorus, so you will be writing 1s2, then 2s2, then 2p6, then 3s2, then 3p3. So 3p3 means what? 3p, it's a p orbital. It's a p orbital, p subshell. And p subshell has how many orbitals? Three orbitals. One, two, three, isn't it? So p subshell has three orbitals. In the same way, d subshell has five orbitals, whose name are dxy, dyz, dzx, and dx square y square dz square. There are five orbitals that are present in the d subshell. And of course, each orbital is having two electrons. This is the maximum capacity of an orbital. You will never see more than two electrons in the same orbital. And altogether, there are 10 electrons in the d subshell. So what's the maximum capacity of a d subshell? I would say 10 electrons. And if you're going to distribute this notation, so I can say D subshell has total five orbitals, and each orbital must have a capacity to, like each orbital has a capacity of two electrons, so the total becomes 10. And also, if you can notice, this is going to be the shapes of the D orbitals. Now you can see these two orbitals, number one and number two. These are the two orbitals which is on the axis. These are the two orbitals which are on the axis like that. This is z axis, this is y axis, and this is x axis. You can see the lobes, they are lobes. This is called lobes. So the lobe is on the y axis and x axis. You can check it. If I can zoom it, so you will see on y-axis the orbital is drawn. On x-axis the orbital is drawn. But if you can check any other, like this one, so the lobe is in is you can lobes are between the axes. If the lobes are between the axes, so this is going to be dxz, dxy, and dzy, like any one of them. But if the lobes are on the axis, like this one on z axis, this one and this one, y and x axis, so then they are going to be dz square and dx square y square. I would be telling you what's the application, what's the use of using these like orbitals and how we would be memorizing it. And when we would be discussing the complex compounds and also the color theory of the complex compound, at that time you will feel that they are very useful. Okay. And also, hopefully you know this concept. Okay, I didn't tell you 4s versus 3D whenever we write the configuration for the transition elements. So we have to end the configuration at 4s. Like 4s becomes after 3D. Like 4s becomes after 3D. Why? Because the energy of the 4s is higher than the 3D. That's the reason. Whenever we write the configuration, so 4s becomes after than 3D. Okay. And after that, and after that, um, we have a very important thing to discuss is the complex compounds. This is very important in this Unit 5 syllabus. Complex means like, we have all other compounds as well. If you can see, we have sodium chloride, we have magnesium chloride, and we have like ammonia as well, sulfuric acid, nitric acid, all organic compounds as well. So, they are something else. And if you will study the complex compounds, they are like something else. And also, uh, these are the compounds. You will see a very unique thing in this. Very unique thing is this. All the complex compounds have dative covalent bonds. All the complex compounds have uh, dative covalent bond. Okay. And also, all the complex compounds, they will be containing metal and a non-metal. Like the metal would be the central element. You know what I mean? Like I'm saying, what is mean by the term central? In ammonia, in ammonia, if you will be writing down drawing the dot and cross diagram, so we generally used to write like that. N, H, H, and one lone pair of electron. So what is nitrogen? What is nitrogen? It's a central element. What is nitrogen? It's a central element. And also in water, when we would be drawing the dot and cross diagram, so the central element is going to be oxygen. So we have some central elements. So the speciality for the complex compound is to have metal as a central element. Remember, that's the difference. That's the difference. Metal as a central element, which is bonded to the negative substances. Not always, but we we give the special name to the non-metals here, that is ligand, through a dative covalent bond, or I can say the coordinate covalent bond. So, normal compounds have simple ionic bond and a covalent bond. Okay. But the complex compound have dative covalent bond. This is the unique thing for the complex compounds. They're not just like a normal compound. They have a very different behavior, you will see. And they are colored. Okay. And also they are very useful. We will be looking at this. So as an introduction, I can say the complex compound is the one when metal is dative covalently bonded with the ligand. Okay, I'm repeating. Uh, what is complex compound? When a metal is surrounded by a ligand through a through a dative covalent bond. So I would say that this is going to be the complex compound. Okay. Um, I'm just, you can say, taking a neutral example, generalizing it. I'm representing the metal by M and I'm representing the ligand by L. And of course, ligand is an electron pair donor. Ligand is the one which is an electron pair donor. Okay, this is the definition of the ligand, electron pair donor is known as ligand. And we have metal. You know, metals have a positive charge, isn't it? Because metal has to lose electron. And after losing electron, they will be having a positive charge. Okay. So, the very interesting thing in this complex is that the metal must have empty orbital. You know why? You know why? If you remember, when we used to discuss dative covalent bond, so we used to have this example. Look at this. Ammonia is reacting with HCl. It would be forming NH4Cl. So then I can make it easy. Ammonia reacts with H plus. It would form ammonium. Now, how I can explain it where the dative bond is. So this is ammonia, one lone pair, and this is H plus. Of course, you all know that H plus is having 0 electrons right now. So it needs two. It needs what? It needs 2 electrons more. So ammonia is giving its lone pair to this H positive ion, and it would be making a dative covalent bond. So how can I summarize it? The thing is that this is going to be the ligand. This is going to be the ligand, and the ligand would be giving its electron to the metal, and the ligand would be giving its electron to the metal. So yes, in this way, the coordinate covalent bond, or I can say the dative covalent bond, is formed. So the one species should be electron rich and another species should be electron poor. Just imagine if the metal doesn't need any of the electron. Just imagine. It's not possible even, but we can make our concept. Like let's suppose if the metal is already fulfilled, like it doesn't need any electron. So what would happen? Because I told you that what's the complex compound in which the ligand is going to donate its lone pair to the metal. The ligand is going to donate the lone pair to the metal. But metal must have an empty space so that it can accept a pair of electron from the ligand and it can make a complex compound that is represented by M and arrow and L. So the representation of organic compound is so the representation of complex compound is M and then L. Now we have to specify this, like what type of metal is present, what type of ligand is present. So I told you the very general formula for the complex compound. And also we have to consider this as well. This is very important before going to start complex in details. M means metal, L means ligand. I would be telling you the types of ligands as well. It can be positive, it can be negative, and it can be neutral. It cannot be positive. And then we have two types of N. This N means the charge. Sometime it's +1, sometime it's +2, sometime it's -1, sometime it's -2. And the next one is the next N means the number of dative bonds with the metal and the ligand. With the metal and the ligand, like the number of dative bonds. Some complex compounds form, you can say, they have 4 ligands, some have 5 ligands, some have 6 ligands, some have 2. Okay. So then at that time, this would be very useful and helpful. Okay, what is N? So N would be telling you about the number of dative bonds between the metal and a ligand. Simple. Or this is a very practical example of a complex compound. We have a copper sulfate. We have two types of copper sulfate. We have anhydrous copper sulfate, and then we have hydrated copper sulfate. Hydrated copper sulfate is blue, but like the anhydrous copper sulfate is a white solid. Anhydrous means there is no water, but hydrated means there is water. Hydrated means there is water. So here in this example, I have just explained how the water is going to donate its lone pair to the copper 2 plus. Okay, so we have total 6 water molecules that are donating their lone pairs to the copper 2 plus, okay. So it is represented by an arrow. Of course, this is going to be the dative covalent bond. Why? Why dative covalent bond? Because oxygen is giving its lone pair to the copper. And when the pair of electron is donated or is shared between the two substances, pair of electron, not one, not one. Remember, it's very important, not one. I'm saying pair, not one. I'm saying pair of electrons. So then, yes, we can say that from 6 sides, if you can count it, 1, 2, 3, 4, 5, 6. From 6 sides, the water molecule can attack on the copper plus 2. On the copper, like plus 2. Only 6 possibilities we have. Only 6 possibilities we have. There would not, you will not see that CuH2O7. No. You can just imagine it if you have a dining table and you have a chairs. But the size of the dining table is very small. But the you can say, okay, first of all, you can see how many pair of electron we have. Two lone pairs, 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 two lone pairs. Okay. So we have multiple lone pairs on the water since water is a ligand. So water would be giving its lone pair to the copper, 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 to the copper. Okay, we cannot attach more than the assigned ligands. So I was telling you that if we have a smaller dining table, so how can you put more chairs around the dining table? Of course, it's not possible even because the size of the dining table is lower. Yes, if we have a larger surface area dining table, a big dining table, so you can you can attach or you can put more chairs, like more than 3, more than 4, more than 5, more than 6. So you can see here in the complex, the size of copper is neither very small nor very large. So it's a 50-50. Or so what we can do, we can attach only 6 water molecules. After 6, we can't attach. After 6, we can't put many water molecules into this. You know, if you are thinking, sir, this is the space the water can attack. Sir, this is the space the water can attack. Sir, this is the space. This is the space. This is the space. This is the space. This is. No. If you will see this in a three-dimensional space, so you will see there is no space even for the coming ligand to attack on the copper and to give their electrons to the copper plus 2 cation. No, there is no space. But in the notebook way, when we generally draw, so we just think about that. Yes, there is a place, there is a space, more water molecules can also attack on the copper plus 2. But in reality, maximum you will say 6, maximum 6 water molecules. It can also be represented by this compound CuH2O, CuH2O6 and plus 2, CuH2O6 and plus 2. You know why 6H2O? Because we have a 6 water ligands. Why? Because we have a 6 water ligands. And the overall charge is plus 2. We would be learning, we would be looking at how to find out the charge like that. Sometime it's +2, sometime it's +1, sometime it's -1, -2, sometime it's having no charge. And what would be the coordination number? Sometime it would be 2, sometime it would be 4, sometime it would be 6, not more than 6, remember. So we have to do these things as well. And let me tell you one thing more. Let me tell you one thing more about the ligand. What the ligand is. Um, yes, generally the student know about the nucleophile. Of course, hopefully you also know what is nucleophile. Nucleo means nucleus. Phile means loving. Loving nucleus. Of course, nucleus has a positive charge. When something is going to attract towards the nucleus, which is positive, of course, the species would be in negative form because oppositely charges attract each other. Okay, this is the reason. And also, ligand is electron pair donor. That's the definition of a ligand, electron pair donor. Let's say we have ammonia. Yes, we know ammonia has no charge, but ammonia has a lone pair of electrons. So yes, ammonia can donate its lone pair of electron. Ammonia can act as a ammonia can act as a ligand. Ammonia can act as a ligand. Remember, ammonia can act as a ligand. This is very important thing to know. And water as well. Water has no charge, but water has a lone pair of electron. Water has even two lone pair of electrons. So water can act also as a ligand. So yes, we can summarize it. Ligands can be negative and ligands can be neutral, but ligands cannot be positive. Ligands cannot be positive if something has a positive charge. So how can it donate their electron? Because positive means no electron. So remember, there are two types of ligands on the basis of charge, on the basis of, I can say, the availability of the lone pair of electrons. So negative ligand, which has a negative charge, you can see OH minus, SO4 2 minus, NO3 minus, Cl minus, Br minus, I minus, they are negative ligands. And we have a neutral ligand, like like something which has no charge but it can donate their lone pair of electrons. This is called I can say the neutral ligands. Okay. And yes, then on the basis of the availability of the lone pair, some ligands can donate one lone pair, some ligands can donate two lone pairs, some ligands can donate more than two lone pairs. On the basis of the availability of the lone pairs, we can also categorize the ligands. Some are monodentate, some are bidentate, some are polydentate. Monodentate means the one which can donate one lone pair, the whole pair. Let's say ammonia. And let's say ammonia. Ammonia means NH3, and on the nitrogen we can see the lone pair of electron. We can see the lone pair of electron. It has only one lone pair of electron. It can donate one lone pair of electron. It's a monodentate ligand. In the same way, we have Cl minus, OH minus, NH3, H2O, Br minus, I minus, Cn minus. If you are thinking, sir, water has two lone pairs on the oxygen, so why you are saying it's a monodentate ligand? Because it can donate two lone pair of electron. No, no, it's a misconcept. Yes, I'm not saying that it doesn't have any lone pair of electron. It has. It has two lone pair of electron, but at a time, remember, at a time, it can only donate one pair of electron. At a time, what I'm saying, at a time, it can donate only one pair of electrons. So that's the reason it's in the category of that's the reason is in the category of like the monodentate ligand. Okay. And then we have a bidentate ligand which can donate two lone pair of electron and makes two dative bonds and makes two. So monodentate can make one dative bond, but bidentate can make two dative bonds. What are the examples of a like the bidentate ligand? C2O4 2 minus. It's an oxalate ion. You know what is this? It's an oxalate ion. Let me write this oxalate ion. Oxalate. It's an oxalate ion. Oxalate ion. Okay. And then we have En. En. What is En? Let me describe it. What is En? So basically En is going to be NH2 CH2. Yes. This is the structure for En. Two nitrogen atoms which has a two lone pair of electron. Then we have two carbon atoms. It's called ethylene diamine. Ethylene, ethylene diamine. It's also a bidentate ligand. You can see it can donate two lone pair of electrons. And then we have a polydentate ligand. Poly means more than two. Poly means more than two. It can donate more than two lone pair of electrons. So you know in EDTA, it's a ethylene diamine tetraacetate. It can donate at a time six lone pair of electrons. You know, it's a hexadentate ligand, but we can't, like, we're not supposed to specify this. If something can donate more than two electrons, so we can say it's a polydentate ligand. Okay, so if you can see the structure for EDTA, it has, like you can say, six lone pair of electrons. One, then two, then three, then four, then five, and then six. It has six lone pair of electrons. At a time, it can give the six lone pair of electrons. So yes, EDTA is a polydentate ligand. So it's a, you can say, we have three types of ligand on the basis of the availability of the lone pair of electron. And we have two types of a ligand on the basis of the charge. Number one is the negative ligand, and another one is the, we have neutral ligand. Okay. Or afterwards, then we have a coordination number. What is coordination number? Coordination number means number of dative bond formed by a ligand. You know, number of dative bond formed by a ligand. Some ligands can form one dative bond. They are known as monodentate ligands. Some ligands can form two bonds. They are called bidentate ligands. Some ligands can form more than two bonds. They are polydentate ligands. So the number of dative bonds, the number of dative bonds, the number of that dative bonds formed by a ligand with the metal. The number of dative bonds formed by a ligand with the metal, they will be known as coordination number. So everything is fixed in this one. If the ligand is making only one dative bond, so this is fixed for a ligand. We can't change it. Some ligands can form more than one bond. Let's say we have C2O4 2 minus, which is a bidentate ligand. It can form two dative bonds. So this is fixed. You will never see that if something is going to make two dative bonds in one compound and it would be forming one dative bond in another compound. It's not possible. Everything is fixed. Like if we have EDTA, it can form six dative bonds. So this is fixed. What you have to do, examiner will be giving you the compound and will be asking to identify the coordination number. You know, coordination number is this. Like coordination number is this one. Every complex compound will be having metal in a ligand. So you will see the number with the ligand, not with the metal. Okay, not with the metal. So this is 3. This is 3. This is 3. So I can't decide after looking at this number whether I can say it's a whether I can say coordination number is 3 or something else. We have to determine the nature of a ligand as well. Is this a monodentate ligand or a bidentate ligand or a polydentate ligand? Since in this question it's En, as I told you that En is a bidentate ligand. If it's a bidentate ligand, so it can make two dative bonds, isn't it? If it's a bidentate ligand, it can make two dative bonds. So what if we have three ligands? If one En can make two dative bonds, so the two En can make four dative bonds. So if we have three En, so how many dative bonds it would be forming? You will say six dative bonds. So yes, so the coordination number is going to be 6. You can see the coordination number is going to be 6 until or unless what the number is written over there, but still you have to find the nature of that ligand because yes, if we have a monodentate ligand, so coordination number would be 3. That's okay. But in this question, the given ligand is a bidentate ligand, so then we have to multiply this by 2. And what if I have this one? No, no number is there. Like, of course, we can consider that it's going to be 1. So we have EDTA. EDTA can donate 6 lone pair of electrons at a time. EDTA can make 6 dative bonds at a time. So yes, the coordination number is going to be 6. This is conceptual thing, without looking at the number, you have to first find out the nature of the ligand, what the ligand is. Is it monodentate or is it bidentate or is it a polydentate? Okay. Then afterwards we can determine the coordination number. So first of all, we must know about the nature of the ligand.